Okay, let's get started. So I'm going to continue with information theory today, and I'm going to focus entirely on just one thing, which is source coding. And as you know from reading the text, this is how we encode messages from a source. So I want to first remind you again the difference between messages and symbols, because actually it turns out to be quite important in practice. And then once we go back to understanding what messages are and symbols are, I'll give you the just an overview of what a message source is, and then corresponding to it what codes are, and then the representation of codes in the form of trees, which allows us to compute what's called the Kraft inequality, and then the expected expected length of an optimal code, which is lower bounded by the entropy, and then a specific coding algorithm that you could use if you knew the message probabilities up front. It's called the Huffman code. It's an example of a greedy algorithm for coding. So let me start again and remind that we have this notion of a source, a message source, which is creating messages that is going to be sent on some channel to one or more receivers. And so this is always going to be the model for information theory. Today what we're going to do is we're going to ignore the channel and ignore the receivers and focus purely on the source, and that's why we calling it source coding, because we're focusing only on the source. Later on, we'll study something called channel coding, which is how do we code messages that are going on a channel, okay, which is different from source coding. And in fact, both have to be done. You have to do both source coding and channel coding. We will see that later. Right now, we're going to focus only on the message source. Okay. Now, last time when we talked about message sources, we discussed this notion that a message source creates messages, and we depict a message source as a random variable x whose domain is these set of messages xi, which could be a finite or infinite set of messages, but we have message set. And so the case would be if you're watching a TV program, you know, basically the entire program is your message set, right? And so we have this problem that this message set is potentially infinite, and we have no idea we can't associate any probabilities with any particular message, because, you know, it never repeats, or if you have reruns, I guess it repeats, but we don't have any idea, we can't get our hands around it because there are too many messages. So the trick that we use is that although the messages correspond to, for example, entire TV programs or billboards or whatever, we go to the step of using symbols to represent messages. Okay, and once we go into symbols for representing messages, at least we have some idea what to do. For example, if I take a TV program that's half an hour in length, and I say, okay, what's the message space of half an hour, TV programs that are half hour in length? Well, it could be anything. We have no idea. On the other hand, if I tell you, well, what we have when we have a half-hour TV program is that we have at every second 30 frames being shown to you, right? And each frame consists of, let's say, HD TV, so 1020 by 768 pixels. So it's about 700,000 pixels, and each pixel takes one of 24-bit value. So we kind of get half an hour into 60 seconds per minute into 30 frames a second into 1028 by 764 or whatever it is, 1024 by 768, sorry. Okay, that's the number of pixels, and each is a 24-bit pixel. So that's the total number of bits that I'm going to send to you, right? And so you say, wait there a minute, then all I have is I have this many zeros and ones. Okay? I have this number, whatever it is, I have that many zeros and that many ones. So I just have two messages. The message is a 0 and the message is a 1. Okay, and that's all I have. So all TV programs of length half hour can be broken down into messages that are only 0 and 1, but that's too little structure, right? That's just too little structure, because I can tell you the probability of a 0 is something and the probability of 1 is something, probably the equivalent, right? It's 0.5 probability of 0, 0. Probability of 1. I have nothing to, I can't do anything with that, okay? So what we can do then is to say, all right, what we'll do is we'll take out this 24-bit. Now I have got 2 to the 24 different colors that I can represent, right? So that I can look at the probability of each color. I can say, okay, I'm now going to choose a symbol alphabet of 2 to the 24 symbols, okay? Or I can take up the screen and I can divide it up into little chunks which are larger than 1 pixel, okay? Let's call these blocks, because that's what they use in MPEG, which are, let's say, I don't know, 16 into 16 pixels. And then each is 24 bits. So this is, now I'm getting a much larger set of symbols to deal with. I can say, okay, that's a set of symbols, okay? So what happens is that the same set of messages can be represented by symbols which are progressively longer. And the more the symbols we have, the more structure there is, okay? And the more sort of we can do with it, more we can do with it, as we'll see in a minute. But if it's too long, then it becomes infinite. Then we really have no idea, right? If you take, well, the space of all possible movies of length half hour, or all possible TV programs of length half hour, it's too much. But I can certainly talk about what is the probability or the frequency of different colors, or the different kinds of blocks, the frequency of blocks of this many pixels, 16 to 16 pixels. For example, you know, I probably will have many color, you know, if I have a lot of nature programs, presumably there's a lot of these blue or green, you know, corresponding to sky or trees. I can say, well, that's a, if I just send 1 bit of information, this is blue, then you can get that whole 16 by 16, because when you look at, so we'll see what that means in just a moment. I just want to kind of set the stage for what we're doing by saying that we go from this messages, which is equivalent to, let's say, 30-minute TV programs, and we have to make a choice, and this is really a representation choice, a modeling choice of symbols which constitute those messages, okay? And so what we then do is that once a choice is made, we're going to slightly change our viewpoint and view this symbols or sets of symbols, or maybe we should call it symbol sequences, and we're going to view these symbol sequences as the messages. Okay, we're not going to look at the main messages, we're going to look at the symbol sequences of messages, and then we'll have something doable in terms of probabilities of each particular symbol sequence. Okay, so to again take another analogy, if I tell you what's the space of all possible books of length 100 pages, that's pretty much impossible to tell you. It could be anything. But if I tell you that, no, I just want to know the frequency of the letter E in books of length 100 pages, that's doable. We can sample it and do it. If I want to tell you the diagram, you know, EF, or I want to tell you the trigram ABC, etc., we can find these trigram frequencies. That's exactly what I'm doing over here. Okay. So in dealing with information theory in a practical problem, when you have a set of messages, you have to make a choice of what symbols do you use, and it can't be too small or too large. If it's too small, then you just get all zeros and ones. And if it's too large, then the space is too vast. You have no way of quantifying it. Okay. All right. Are there any questions about this over here? Okay. So having said this, we now are going to kind of assume that we've got some random variable x, which corresponds to some domain of messages or symbol sequences x sub I, and associated with this is the probability of each message, which is p of x sub I, and we have this given to us somehow. Okay, so our goal then is to transmit this or save this message on a file. So let's say I give you a text, you know, I give you the complete works of Shakespeare, and I say store it on a drive for me, hard drive for me, and try to take the least amount of space. So what you want to do then is to come up with a scheme which uses the least amount of space, basically, and that's what source coding is all about. So source coding tries to minimize the message length, or I should be more precise, minimize the coded message length. And the way we do it is that for each x sub I, the message, we're going to compute some code word. Okay? And in expectation, the code words are chosen such that the expected message length or the expected coded message length is minimized. So the expected value of the coded message is, so you want to minimize that. That's the project. We want to minimize the expected coded message length. Okay. So how do we do this? We basically compute for each xi something called C of xi, where C of xi is the coded message, so that's the message, and this whole thing is the coded message. And so there is a unique function from xi to this, and this is basically going to be the symbols, the codes are chosen from a code book, from what's called a code book. Okay, and that's just a mapping from a message to the string. And for all purposes, we'll just can look at the set 0, 1 plus, which is basically all strings of non-zero strings, which consists of zeros and ones. So any code with any symbols, I can always represent them as zeros and ones. So, I just ignore all the other symbols. I don't need to use any particular symbols. I'll just say I'll just use 0, 1 for everything. Okay. So obviously we can do that. So we will. Okay. So all right. So for example, if you were to do English text, you could take the if you could say, well, A corresponds to 0, 0, 0, 0, B corresponds to 0, 0, 0, 1, etc. How many bits do we need in this code length? Well, if you have 26 alphabet plus space, so that's 27, then we need at least 5 bits. Otherwise, we don't have enough, so I guess I need one more over here. So we can just get a bound on the mean, on the code length, simply by saying, well, how many do we have, right? But this may not be the best way to go, as you'll see in a minute, okay? So if I just go a naive thing, I'll say I need 5 bits, okay? Because I need 32 different things. But that may not give you the mean expected code word, because the messages have different probabilities, okay? So for example, A has a high probability and Z has a low probability. I could give Z a very long number of bits. I could give it 10 bits even and give A only 1 bit. That would still, in the way, it would work out for me, right? So having all of them have the same code word length is actually not a good idea, okay? And we'll see that in just a moment. But before we do that, let's just study what a code is, just from the perspective of an abstract code. And for that, I'll introduce a couple of terms, and then we can have this homework problem on that. So the first study of a code, we're not talking about how the coding is done. Coding is done in some arbitrary way. It's given to you. Somebody says, here's the code book. It's a message. Here's the code word. And you take a look at it and you say, okay, first, is it unambiguous? And is it instantaneous? Okay, these are two things you can answer, whether for any code without having to know whether it's optimal or suboptimal or good or bad or whatever. I'll just give you a code book, you take a look at it. And unambiguous means that no two messages go to the same code, right? So if I have a system where A goes to the code 0, 0 and B also has the code 0, 0, then I'm in trouble, because if the receiver sees 0, 0, they don't know that's A or B. Okay, that's not a good idea. So obviously we can tell whether it's unambiguous or not. A second thing is instantaneous. Instantaneous means that if we have the code word, if I see the code, let's say I get the code 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, something like that. And as the receiver reads through this, it can kind of chop off the pieces and say, that's the first code, that's the second code word, that's the third code word, that's the fourth code word, etc. Okay? If it can do that, it's instantaneous. Okay, you don't need to go back and say, oops, that really wasn't the code word after all. Okay, what I really should have done when I get back here is say, I really should have put the boundary over here, and I'm going to have this as the code word. So you have to go back and sort of redo things. Okay, if you have to do that, it's not instantaneous. So instantaneous basically means as the receiver is getting the codes, getting the codes on the channel, it can invert the process and recreate the message, okay, without having to go back and do any work. Okay, so to illustrate this, let's look at this code book where I have the message symbol over here, and this is the code word. So this is a code book. It's just a table, and it says A is 1, B is 0, 1, C is 1, 0, and D is 1, 0, 1. So the first thing is it instantaneous, and is it, okay? So, well, let's see if it's instantaneous or not, right? Does anybody want to answer this? This should be relatively easy. So is it instantaneous? No. Okay, why is it not instantaneous? C and B. So if you see 1, 0, at this point you're in trouble. Okay, it could be a C, or if you get a 1 after that, then it could be a D. So at this point you see if the input is 1, 0, you have trouble. You don't know what to do next. You don't know whether to output C or wait a little bit longer, and if you see a 0, you say, oh yeah, that must have been a C. So you have to see one more symbol ahead, and because of that, it's not instantaneous. Okay. So second question is it unambiguous? Okay, so is it unambiguous?
It is ambiguous.
It is ambiguous. Okay, why is it ambiguous?
1, 0, 1.
Right, so if you see 1, 0, 1, we can interpret it in two different ways. We can interpret it as a D, or we can interpret it as C, A. Okay, so both C, A, and D map to 1, 0, 1. And so consequently, it's ambiguous. Yes? AB. So there's more than one, but one is enough. Okay, thank you. Yeah, AB is 1, 0, 1, and that's also D. So AB. So this is a pretty terrible code, actually. Okay, of course I chose it to be bad. In real life, you may it's not so easy to find, but this was meant to be really terrible. Okay, so those are the answers to those two questions. So it's neither instantaneous nor unambiguous. Yeah. Why is what?
Morse code?
Yeah.
It's not instantaneous.
It's not?
No. E in Morse code is just 1, and that's going to be a prefix of a whole bunch of different other letters.
Okay. So Morse invented his stuff before information theory. Morse code, I guess, is not instantaneous. E is a dot. What is the E is a dot? Is it a dash?
I think it's a dot, yeah.
It's a dot. Okay, I don't know, but Morse, actually, funnily enough, was not that unscientific. Morse code turns out to be nearly optimal, okay, when people look at it. Yes, Daniel?
There's an extra longer space between words in Morse code. So
okay. I see. So E would then correspond to dot space, okay? And so you do have that extra space, okay? In between. If Morse had studied information theory or Huffman coding, as we'll see in a minute, he wouldn't have needed the space. So E is actually dot space. I guess that's right. That's the right way to put it. Yes?
So how do you define unambiguous? Like you say, if none of them maps to the same thing, in which case, in this case, they don't. So.
Well, no. Here it's unambiguous means that there is no code string that can be interpreted in two ways. Okay, so I'm going from sort of right to left. Right, clearly at this level it's unambiguous. A is 1 and B is 0, 1. However, I can find a code string which is 1, 0, 1, which I don't know what to do. I have three different interpretations: D, C, A, and AB. So it's ambiguous. Okay, so unambiguity is not at the level of a single code word, but on message strings, code strings. I'm sorry.
So those codes which are not instantaneous are always ambiguous, right?
The codes that are not instantaneous are ambiguous. No, it's not true. You can find instantaneous codes where they're not ambiguous. It's except that you have to go backwards to fix up a mistake that you made. So you'll say tentatively it's this, and you'll see something more and say, okay, no, I changed my mind, it's something else. But when you change your mind, it is going to be guaranteed to be okay.
So there can be a situation where the code is unambiguous, but it is not instantaneous.
That's correct. You can have unambiguous and instantaneous codes, non-instantaneous codes, correct, yeah. Yeah, so basically instantaneous means that whether I have to go back in time or alternatively I have to wait for more input, okay, to decide. So the way you would do it in practice is you would have a buffer and you have all the codes come in when the buffer is a particular length, let's say 5 symbols. When you have 5 symbols in the buffer, which means current symbol plus 4 future symbols, then you know unambiguously what it is. So it would be instantaneous. It would not be instantaneous because you need a window of size 5. Instantaneous means the windows of size 1. You just have to look at the current symbol and that's all you need to do. Okay, whereas for non-instantaneous you need a longer buffer. And instantaneous codes, again, just sort of a historical note, were important in the context when you had before computers, right? So if before you had computers, you had electromechanical systems receiving the codes and spitting out the message, and you wanted to have a very dumb system. You didn't have memory. Memory was not there. When you don't have RAM, all this becomes very difficult, so you say, I must have an instantaneous code. However, if you're willing to live with a non-instantaneous code, all you need is a bit of RAM. Today, a gigabyte of RAM costs, I don't know what, $5, $10, I don't know, it's something ridiculously cheap, right? So, I mean, that's 1 billion bytes you can put in there, okay? So, the emphasis that information theory places on instantaneous codes is historical, but in my mind it's just archaic. We really don't need to worry too much about it. So I'm going to talk about it because people all emphasize instantaneous codes, but if it were today, I'd say here's instantaneous code, here's a non-instantaneous code, but the non-instantaneous code is better in some respect, more efficient. I'd go with the non-instantaneous code in a moment. I don't really care about having a buffer of 10 symbols. It's not worth thinking about. Yeah. 10 symbols at a bit rate of 100 gigabits per second. Okay, 10 symbols at that bit rate is what, 1/10 of a nanosecond. I really can't be bothered about a delay of 1/10 of a nanosecond. Doesn't really matter. Right? But again, information theory comes from the 1940s and so on, when there really wasn't. So if you go into information theory and you have this huge emphasis on instantaneous code, you should take it to the bit of, yeah, okay, fine, it's instantaneous, but do I really care? Okay, let's get started. So I'm going to talk about optimal codes now. So far in that code book I gave you, we're just looking, somebody gives you a code book, you can say, is it ambiguous or not? Is it instantaneous or not? But now the question is it optimal? Okay, and what does it mean to have an optimal code in the first place? So we're going to talk about actually optimal instantaneous codes, okay? And there are optimal codes that are not instantaneous, but we won't talk about them, okay? But we're going to talk about optimal instantaneous codes. But first, let me talk about 2 intuitive principles for optimality. So what are 2 things that we can use for optimality? So the 2 intuitive principles, and we and the first one has to do with choosing code words for longer symbol sequences. And the second one has to do with code words essentially take message probabilities into account. Okay, so let's start with the first one. Let's assume that you want to, somebody says, write a code for English letters, right? So you have basically A to Z and plus a space. Okay, so we'll just take the 27 over there. And okay, you just say, fine, I'm just going to give you 5-bit sequences. So I'm going to have 0, 0, 0, 0, 0 up to whatever 0, 1, 0, 27. So that's 16 plus 8 plus 3. So 0, 1, 1. That's too many. There's no leading 0. Yeah, 16, 8, 24, 0, 1, 1. Thank you. So that's going to be my code. Okay. Now, that is a reasonable code, but let's take a look at some of the things you could code with this. You could code the string qx corresponds to some 10 digits, 10 bits, I'm sorry. Okay, but you're never going to see qx. Okay, I mean, unless it's some kind of action movie and qx is the name of some fighter plane or something like that. You never see qx, right? So that's a wasted code word. You're never going to have that message, yet it's taking up space. And probably you're going to have things like, xz and, z or q and all this other stuff. There's quite a bit of many diagrams, quite a few diagrams, which are going to be given code words, which are going to be coded by this in this code, but they're never going to be used. So it seems intuitively true that if I didn't have these codes, I could have shorter codes, the fewer ones, right? So I could instead then say, look, I'm not going to code this way. I'm going to code diagrams. I'm going to have code for AA, one for AB, one for AC, etc., all the way up to AZ. And then I have BA, etc., all the way down until I have space, space, which is the last one. However, I will not assign code words to those diagrams which don't show up. Okay, which are not messages. Okay, the probability of that message is 0, or which just don't show up. I'm just going to eliminate them. Okay, if I do that, it turns out that I'm going to need fewer bits. Okay, the other thing that's going to happen is that we have this problem of integrality constraints on the code words. So the first lesson is if you take longer symbol sequences, we're eliminating things that we don't need. We can make our code words shorter. So I can come with a code, I can take a code book, and if I take a longer sequence, basically I have way more symbols in the code book. Size is going to get squared, right? If I have a code book of size n, then I need a code book of size n square, but the code word, the mean code word length is going to be smaller, right? So that's how I get towards optimality, and in the limit I can take a code book that's infinitely long, well, it's as long as the message size, and then I'll get sort of the smallest codes possible. But then it's going to be a very, very large code book. The second thing is that we have integrality constraints. So let's say I want to code for the numbers between 0 and 10. So 0 is 0, 0, 0, 0, and so I need, so and then 1 is 0, 0, 0, 1, all the way up to 9, which is going to be 1, 0, 0, 1. Well, I use 4 bits. I could have coded up to 15, right? 0 to 15. But I didn't use the remaining ones. So I have this wasted space basically over here which is not being used. And that's wasted just like this is wasted. So here I'm coding for things that are never going to happen. Here I also have coding, I'm coding things that aren't going to happen either. So I'm wasting space there, wasting space in the code space. Okay. So if I were to code instead for 0, 0 all the way up to 9, 9, I need basically 7 bits for this. Is it 7 or 6? It means 4. Yeah, I need 7 bits for this. And so but here per symbol I'm using 4 bits. Here per symbol I'm using only 3.5 symbols, 3.5 bits, because I have 2 symbols and 7, so it's 3.5. So my coding efficiency is 3.5 bits per message symbol. So it gets better, right? Again, from 4 down to 3.5. This is 4, this is 3.5, which is good. And similarly over here, I'm going from 10 bits down to, let's say, 9 bits if I use this. So these are 2 ways I can certainly improve my coding efficiency. Okay. So that's code words for longer symbol sequences. Allows me to get rid of these integrality constraints, right? Because I can't have 3.5 code bits over here. I'm always going to have something like this. I'm always going to have 4 bits or 3 bits. I can't have 3.5, so I'm going to have to pay that price, and then I'm going to code over here. So these 2 things allow me to code by using code words for longer symbol sequences, I get, on average, better code words. Okay? So, any questions about that? Okay. The second thing that can help is for me to take message probabilities into account. So, I mean, to take a very simple example, let's say that I have two messages, and one of them is hello, and the other one is goodbye. Okay, actually, let me take three messages, and okay. So let's say you have three messages, and this happens with probability, 0.99. This happens with probability 0.005, and this happens probably 0.005. One possible code book would be to say, this is the probability, would be to give this 0, 0, 0, 1, 1, 0. Okay? But that would be a stupid way of doing things, right? Instead, if you do another code book which says 0 is this is 1, 0, this is 1, 1, for the sake of argument, okay? What's going to happen is that since most of the time I'm just saying hello over and over and over again, I only have to send one bit, right? So in some sense, we can see that this is a better code book than that. Okay, this is better than that because if you take the expected message length, the expected message length is over here, the length is 1, here the length is 2, here the length is 2, here the lengths are 2, 2, and 2. So the expected message length for the first case is going to be 2 times 0.99 plus 2 times 0.001 plus 2 times 0.005, sorry, equals 2. Well, obviously, that's going to be the case because it's always 2. Here, my expected message length is basically 0.99. So, 1 times 0.99 plus 2 times 0.005 plus 2 times 0.005, which is whatever, it's fairly small. It's 1 point something, 1 point really something small, right? So, the expected coded message length, okay, is smaller over here, okay, and so we say that this is a coded, this is better code. The other way of thinking about it is that what is the expected code word length? We can view it the same way. So the expected code word length is going, because we have so the expected coded message length is going to be just given by this. Okay, so let's call this one L1. L2 and L3, then the expected length is going to be nothing more than sum over I, probability of the message I, xi, and then the li. Okay, so this is going to be, and we'll call that E. E is the mean coded message length. Okay, and so if we knew this over here, which we can approximate by taking a corpus of messages and taking longer symbol sequences, etc., but for now we're just given some x. So this is x, and this is x1, this is x2, this is x3, and then this is p of x sub I. Okay, so given the random variable x representing the message source, and given the different values it takes, this is the domain D of the random variable, and this is the probability mass function of the random variable x, we can certainly compute the expected coded message length given the code book. Okay, so our task now becomes basically choosing the code book such that this is minimized. We want to minimize this quantity right here. Okay, and I'm going to put it in a box so that we don't forget it. Okay, and that would be called the optimal coded message. Okay, and any questions about this over here? So in the next 20 minutes or so, I'm going to show you how to compute this. Actually, by the end of the class, you'll know how to do this using an algorithm, using the Huffman code, which you've seen in the text. But let's do that step by step. So, but is this clear so far? Okay. So let's go back to using these principles. We're going to try and use. So we're not going to be able to do much about this, because that's a sort of a choice of what symbol sequence to use, but you're going to use this over here. And what I'm going to do is I'll switch the representation of the code book to something a bit more intuitive, and that will allow us to compute things nicely. So the representation is going to represent codes as trees. Okay, so we've already made the choice that all code words are represented from 0, 1. Okay, so I can draw a tree like this, and this is the root, and the left hand by convention is always 0, and the right hand run is always 1. Okay, so I have 0, 1, 0, 1, and so on. And every code corresponds to either a terminal or a non-terminal node in this tree. So it's either a leaf or a non-leaf node in this tree. So to go back to the homework example,